Imagine standing on a beach at night, gazing up at the sky. Above you stretches a tapestry of stars, each one a sun like our own, perhaps with planets orbiting around it. The Milky Way arcs overhead, a glowing band made up of billions of stars. You might feel small, almost insignificant, pondering the vastness of the universe. With so many stars and possibly even more planets, is it possible that Earth is the only place where life exists? If the universe is so big and so old, why haven't we found any evidence of alien life? This question is at the heart of what is known as the Fermi Paradox, a puzzling contradiction that has intrigued scientists, philosophers, and thinkers for decades. To delve deeper into this paradox, let's first consider just how vast the universe truly is. Our galaxy alone, the Milky Way, contains an estimated 100 to 400 billion stars. Beyond that, the observable universe is home to at least 2 trillion galaxies. If even a small fraction of stars host planets, and if even a smaller fraction of those planets are capable of supporting life, the number suggests that life should be abundant throughout the cosmos. The sheer scale is mind-boggling, and it's hard to imagine that Earth is the only oasis of life in this immense expanse. In the early 1960s, astronomer Frank Drake sought to quantify this possibility. He devised an equation, now famously known as the Drake equation, that attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The equation isn't meant to provide a precise number, but rather to stimulate scientific dialogue by breaking down the daunting question into more manageable components. The Drake equation considers several factors: the average rate of star formation in our galaxy, the fraction of those stars that have planetary systems, the number of planets per star that might support life, the fraction of planets where life actually arises, the fraction of life forms that evolve into intelligent beings, the fraction of civilizations that develop technologies that release detectable signs into space, and finally, the length of time such civilizations release those signals. Let's break down these factors one by one. First, the average rate of star formation in our galaxy. Estimates suggest that about 1 to 3 new stars are born in the Milky Way each year. Over the galaxy's lifetime, that's billions of stars, providing ample opportunities for planetary systems to develop. Second, the fraction of those stars with planetary systems. Thanks to advancements in astronomy and missions like NASA's Kepler Space Telescope, we now know that planets are quite common. Most stars are believed to have at least one planet orbiting them. Third, the number of planets per star that could potentially support life. This involves the concept of the habitable zone, the region around a star where conditions might be just right for liquid water to exist on a planet's surface, a key ingredient for life as we understand it. Fourth, the fraction of those planets where life actually emerges. This is a significant unknown. While life appeared relatively quickly on Earth once conditions were suitable, we don't yet know how common abiogenesis, the process by which life arises from non-living matter, is elsewhere. Fifth, the fraction of life-bearing planets where intelligent life evolves. Again, Earth provides only one data point. It took billions of years for intelligent life to develop here, and we don't know how common this progression is in the universe. Sixth, the fraction of civilizations that develop technology that releases detectable signs of their existence into space. This includes radio transmissions, laser pulses, or other forms of electromagnetic communication. Finally, the length of time such civilizations release detectable signals. Human civilization has been broadcasting signals into space for just over a century, a mere blink in cosmic time. If other civilizations have similarly short technological lifespans, the chances of overlapping with them are slim. Each of these factors carries uncertainties, some more so than others. However, even with conservative estimates, the Drake equation suggests that there should be numerous civilizations out there capable of communication. This brings us back to the Fermi Paradox. Given these high probabilities, why haven't we found any evidence of extraterrestrial life? Many scientists argue that extraterrestrial life should be common, not just because of the numbers, but also due to the principles of mediocrity and uniformitarianism. The idea that Earth's conditions and history are not exceptional or unique. The discovery of extremophiles on Earth, organisms that thrive in conditions once thought uninhabitable, expands the potential habitability of environments previously dismissed. Moreover, exoplanet discoveries have revealed a diverse array of planetary systems, some of which may harbor Earth-like conditions. The age of the universe adds another layer to this argument. At approximately 13.8 billion years old, the universe has had plenty of time for life to develop, evolve, and possibly advance far beyond our current capabilities. If civilizations have arisen elsewhere, some could be millions or even billions of years older than humanity, potentially possessing technologies we can scarcely imagine. Yet, despite the statistical likelihood and the vast stretches of time, we remain alone in our observations. One compelling explanation for this is the Great Filter theory. The Great Filter suggests that there's a stage in the progression from simple matter to advanced life that is extremely difficult to surpass. This filter could be any of the steps in the Drake equation. If the Great Filter is behind us, it could be that the emergence of life itself is incredibly rare. Perhaps the leap from non-living chemistry to the first self-replicating molecules is an exceedingly improbable event. Alternatively, the transition from simple prokaryotic cells to complex eukaryotic cells might be the bottleneck, a step that took over 1 billion years on Earth. On the other hand, if the Great Filter is ahead of us, it may spell a more ominous future. It could be that intelligent civilizations inevitably self-destruct before they can spread beyond their home planets. This self-destruction could come from nuclear war, environmental collapse, pandemics, or uncontrolled artificial intelligence. The Great Filter ahead implies that the silence we observe is a warning about our own potential fate. Another angle is that while microbial life might be widespread, intelligent life is exceedingly rare. The evolution of intelligence is not a guaranteed outcome of natural selection. On Earth, it took a series of highly contingent events for humans to evolve. If this pathway is uncommon, then perhaps intelligent civilizations are few and far between. Moreover, it's possible that intelligent life doesn't develop technology in a way that leads to detectable signals. Ocean worlds, for instance, might harbor intelligent species that never develop electronics due to their aquatic environment. Alternatively, advanced civilizations might have technologies that are beyond our comprehension or detection capabilities. Beyond the Great Filter, several other hypotheses attempt to explain the Fermi Paradox. The zoo hypothesis posits that advanced extraterrestrial civilizations are deliberately avoiding contact with us. Much like wildlife reserves on Earth, they might be observing us without interfering, allowing humanity to develop naturally. This could be due to ethical considerations, similar to our own policies of non-interference with uncontacted tribes. The rare Earth hypothesis suggests that while simple life might be common, the conditions required for complex, multicellular life are extraordinarily rare. Earth's stability, its protective magnetic field, the presence of the moon stabilizing our axial tilt, plate tectonics recycling nutrients, all these factors might be exceptional. If so, then Earth-like planets with complex life forms could be 1 in a billion occurrences. Technological limitations are another consideration. Our current methods of searching for extraterrestrial life are relatively rudimentary. We're primarily looking for radio signals within a narrow frequency band and searching for biosignatures on exoplanets, using telescopes that are just beginning to have the necessary resolution. Advanced civilizations might use communication methods beyond our technological horizon, such as neutrino signals, gravitational waves, or quantum entanglement, which we either can't detect or don't know how to interpret. There's also the possibility that signals have been sent, but we haven't been listening long enough or in the right way to receive them. Our planet has been capable of detecting extraterrestrial signals for less than a century, a tiny fraction of cosmic time. Signals could have passed by Earth before we had the means to detect them, Or they might arrive in the future long after our civilization has changed or even ceased to exist. Some theories even suggest that life on Earth might be the result of panspermia, the idea that life was seeded here from elsewhere in the cosmos. If true, it raises questions about the distribution of life in the universe and whether life-bearing materials are spread widely through mechanisms like comet impacts. Despite these challenges and uncertainties, the search for extraterrestrial life continues with vigor. Organizations like SETI, Search for Extraterrestrial Intelligence, employ arrays of radio telescopes to listen for signals that could indicate intelligent life. Space agencies are sending probes to Mars and moons like Europa and Enceladus, where subsurface oceans might harbor microbial life. The upcoming James Webb Space Telescope and other next-generation observatories aim to analyze the atmospheres of exoplanets for signs of life, such as the presence of oxygen, methane, or other biosignature gases. The Fermi Paradox remains one of the most profound and thought-provoking questions of our time. It forces us to examine not only the cosmos, but also ourselves, our place in the universe, our future as a species, and the very nature of life. Are we a cosmic accident, a solitary beacon of life in a vast, empty universe? Or are we one of countless civilizations, each grappling with its own challenges and limitations? As we stand on the shores of the cosmic ocean, the silence may feel deafening, but it also drives us forward. The quest to understand our universe and to find others like us is a journey that transcends science. It's a fundamental part of the human spirit. Whether we eventually find evidence of extraterrestrial life or not, the pursuit itself enriches our understanding of the universe and our place within it. So, as we continue to peer into the depths of space, building more advanced telescopes, sending probes to distant worlds, and listening for whispers from the stars, we keep the hope alive that one day we might find the answer. Until then, the question remains open, inviting us to explore, to learn, and to reflect on what it means to be part of this vast and mysterious cosmos.